and he received his PhD in atomic physics from the University of Strathclyde in Glasgow, 2005. And then he worked at various places, Columbia University and NRL, a Naval Research Lab, where he worked on the Hinode science team. And then at the Goddard Space Flight Center, where he worked on SDO. And his research focuses on solar spectroscopy and for the study of solar atmosphere, and has worked on providing fundamental atomic data for studying corona, CME, fast outflow, and active region. And today he's going to discuss use comets as solar probes.
Okay, is the mic working all right? Yeah. Okay, so this is kind of a little bit different from work I'd normally been doing, but it was kind of like surreptitiously we saw comets using AIA, so we thought, what can we learn about the sun from these comets? So this is work mostly done with Dean Pesnell at NASA Goddard, and Barbara Thompson and Wei Liu were also involved in some of the work here. So this image here is Comet Ison, which we were very excited about because we'd observations of this comet 6 months in advance of perihelion when it was way out by Jupiter. So we thought we were going to have great things from it, but eventually it broke up and fizzled away before it reached perihelion, so we didn't see it in the solar images. But I thought this was a really cool image, so I still wanted to show it to begin with. But that's the last time I'll speak about ISON. Okay, let's start with a little bit of an introduction to sun-grazing comets. They've been seen for quite a long time. One of the most famous is this great comet of 1680, which back in these days, people didn't really understand the orbit of comets at all. Kepler thought they just moved in straight lines. And this comet was seen twice, one in November as it moved towards the sun, and then again in December moving away from the sun. And John Flamsteed at that time, who was the Astronomer Royal, postulated this must be the same comet. So he spoke to Newton about, can you understand what's going on here? Flamsteed's idea was that the comet went towards the sun, and then the magnetic action of the sun reversed and repelled it again. They didn't understand that comets were the same, moved in the same like gravitational attraction as the planets. So at this time, this is when Newton was kind of formulating the Principia, and he used observations of this to refine his R-squared law of universal attraction. So there's other ones that have been spotted over the years, but they're not very common, and that's because when we only had ground-based observations, the comets had to be really big and bright to be able to see them. So when we eventually had space-based satellites, this idea of the sun-grazing comets being rare totally changed. The satellite that has actually spotted the most sun-grazing comets, it was not a cometary satellite at all, but it was SOHO. And the LASCO instrument has seen comets coming very close to the sun on the order of almost one a day. But for the majority of these comets are very small, so it's hard to pick them up in the LASCO images, and when they get close to the sun, they are so small that they just fizzle away, and they've never survived perihelion passage until the two comets that I'll talk about going on. So the majority of all of these comets come from one large progenitor comet, which was of the order 1 million years ago. That passed close to the sun and broke up and resulted in lots of little fragments that kind of continue now on the same orbit. And these are the Kreutz family comets that the vast majority of these 2,500 observations are from. So let's start now. This is the first comet that we saw with SDO, and This was the Glasgow image of the comet approaching. So see it kind of coming in here, close to the sun. And at this stage, we'd never expected to see comets with SDO and the EUV, but it looked like the orbit of this was kind of getting very close to the disk of the sun. So we thought, let's go and look and see what we find. This is just the same. This is just the C2 and Glasgow now, kind of getting a bit closer. So you do notice that the comet comes in towards the sun, but it doesn't come back out. So at some point, it's broken up or fizzled out here. So if we look at the AIA images, kind of hard to see here, but this is AIA 171, and the comet kind of comes across here really closely. Yeah. So it's pretty, but we can definitely see something there. And we've got great. There's we see EUV emission from comets. We didn't really understand why we saw this, but then not long after that, we saw this other comet, Lovejoy, which this was about 5 or 6 months later, and we had advance notice of this comet coming in, so we could position SDO accordingly. This is on the same orbit as the previous comet, but it's just, so it's one of these Kreutz sungrazers, but it's on a different trajectory. It's on the same trajectory, but we are 6 months later, so SDO is around the other side of the sun. So first of all, you notice that the Glasgow images are a lot brighter than the previous one. This is a much larger comet. This time, the comet was behind the disk of the sun from our point of view. And also, we see that it survived perihelion this time. So this is the first ever sungrazer that we've observed to pass by the sun and survive and go back out. Actually, about 2 weeks later, it eventually broke up and fizzled away. So it didn't. It's not survived to make another passage. So I should point out here that all of these, the Glasgow images here, this is white light. So this is just sunlight reflected off the dust in the comet, and that's what we see, which is different from what we see in the EUV AIA images. So I'll get to that in a second. But if you notice, it's bright, and then it fades away as it gets close to the sun, and then we see it again after it passes out. And that's because when the comet gets too close to the sun, these dust particles break up very fast, and they don't exist long enough for the sunlight to be reflected from them. So now look at what AIA saw from this comet. It's a lot clearer now than the previous one. So this is the ingress phase. The comet's kind of coming in from here, goes up here, eventually passes behind the disk of the sun. So we knew this comet was coming, so we were able to off-point SDO so we could track it for longer. So the ephemeris we had for the comet was off a little bit, and we kind of mistimed. We moved back to solar pointing a bit too early, but this actually turned out to be pretty fortuitous because we didn't expect the comet to survive perihelion because none of these ones had survived before. So we actually got back to sun center in time to see it come out the other side. So this is the disk again, and then it's passed behind the disk and then comes out here. So yeah. Distance of closest approach is 0.7 solar radii from the surface, which is somewhere behind the disk here. The perihelion was back there. This, from what you see here, the furthest away it is up here is something like, I think, 2 solar radii from the surface. Yeah, this is like, I put a radial filter on this so that it's not. So there's lots of cool things happening here. You see there's wiggling around, there's little striation things, and you kind of see the emission here hanging around for quite a long time. So I'll get back to explaining maybe what that tells us about the atmosphere it's passing through, but let me, from when it appears here to when it passes out, there is something like 20 minutes, I think. But this, and I'll come back to this later, but this emission here that you kind of see, you see the comet disappears off there, but this emission stays for a long time. So that hangs around for about 40 minutes before it returns to the background level. So I wanted, I guess most people in here will kind of know all about this, but I wanted to give a kind of quick background on the instrument that we use to observe this, because this is all the AIA telescopes on SDO, and we have different filters on the telescopes that measure different wavelengths, and these are used to measure different temperatures of the corona. So this is what we normally view when we're looking with AIA. So this is helium-2, and then the rest of them are mostly sample strong ion lines. And this ranges from like 10,000 Kelvin up to 10, 20 million Kelvin. So this is, when we look at these images, we expect that it's mostly iron emission that we see. And then the question is this the same for the comet? Are we also seeing iron emission from the comet? If it was, we would expect cold stuff comes off the comet. As it heats up, we might expect to see some sort of delay as it passes through these channels. So the comet material comes off cold. We see it bright in these channels, and then as it interacts with the atmosphere, does it heat up, and can we see it passing through in this direction? So to look at that, this is kind of the same image as I showed before, but this is 171, and then simultaneously the 304 channel. And you notice that they're kind of quite different in morphology. This one's like kind of extended emission over a wide range, and the 304 is kind of more compact and closer to the comet nucleus. And if we look at this, the same thing in a variety of the channels, just a snapshot in time, this is what we see. So the 304, what are considered, usually considered the cold channels, we see like small localized emission close to the comet. 211, which is somewhere in between, and then the hotter channels, we see like much more elongated emission that lasts a longer time and is further from the nucleus. So first question is, can we explain why we see emission in the EUV at all from comets? And then does our explanation match with why we see the different morphology in the different wavelengths? There's never really expected to see EUV emission from comets. We've seen them in the X-ray before, and that's like out at maybe 1 AU, which is explained by charge exchange with the solar wind with cometary neutrals. But this close to the sun, cometary neutral molecules don't exist, or neutral atoms don't exist very long. It just gets ionized very fast. So we need some different mechanism to explain the emission here. So this is kind of cartoon model of how we've explained this. So these are just, this is the passage of the comet. We kind of represent it as a cylinder. The comet nucleus is somewhere in the center here, and then the emission is around it. So we take a cross-section of that. The material comes off the comet through sublimation when it gets close to the sun. About 50% of the water, of the comet mass is water. So if we just think about water to begin with, comes off the comet with some V out, some velocity as it kind of propagates into the atmosphere. And then when it gets into the solar corona, it starts interacting with the electrons and the protons of the corona. So for water, the first thing that happens is photodissociation with the solar radiation field. So this breaks up to give us the neutral oxygen and hydrogen. And then as this material expands out, the neutral material gets further ionized. So I'm just following the progression of oxygen here to begin with. So oxygen gets can charge exchange with coronal protons and gets ionized by electrons. This is like very fast, like less than 1/10 of a second, and with typical coronal densities. And then as the material expands into the atmosphere, it just kind of further ionizes, and at the same time, it's getting further from the nucleus. We get oxygen 2+, 3+, etc. So we can track this material passing through its ionization stages as it expands. So this is for oxygen, because this is the most abundant element we have in the comet. But we can calculate the time scales for every element that's constituent in the comet. So we don't have measurements of this exact comet, but there are in situ measurements of comet Halley, and elemental abundance of comets is thought not to vary much from comet to comet. So we use the elemental abundances from this comet and then track the ionizations of every element available. Then using Chianti, we can work out how much emission we would expect to see in each emission line from each of these ions. So the important part is that the amount of emission we see from each ion depends on how long that ion exists. If we get oxygen 2+, for instance, we see emission from that, but that's quickly ionized to oxygen 3+, and then so the amount of time it exists in each ionization stage determines how much emission we see from it. So here's a list of the elements we examined. Hydrogen is actually the most abundant, but that's very quickly ionized, so it doesn't contribute to the emission at all. And then the other elements have various abundances. Carbon's pretty abundant, as well as oxygen. But we just look in the wavelength ranges of AIA telescopes. None of these elements contribute much. So it's mostly from iron and oxygen. So iron is basically the wavelength ranges of the AIA telescopes are chosen to pick up strong iron lines. So that's why we see lots of iron, and oxygen is mostly visible just because it's so overabundant in the comet compared to the corona. So to take these values and translate that into what do we actually see in the AIA telescope. This is the 171 channel. This is the effective area of the channel. Under normal quiet sun conditions, we see this iron 9 line around 171. So then if we take a typical coronal density of 10 to the 8, and then figure out how much emission comes from the comet material, and we see this. So the red is iron emission. This is the same line here, but we've got extra abundance of iron now coming from the material from the comet. And we also have this extra oxygen material coming from the comet. So we see different emission lines contributing to the AIA passband. And we can do the same thing for the different channels of AIA. So this is 304, 193, 131, and 171. So it's mostly oxygen that's contributing. There's some iron. But the important thing is that it's different ionization stages of oxygen that are contributing in the different passbands. So for 304, for instance, it's mostly oxygen 3, oxygen 5 in the 193, oxygen 6 here, and then 5 and 6 here. So if we go back now to try and look at the spatial extent of the observations, you remember before I had these kind of arranged in temperature as we normally view them when looking at iron emission in the corona, and that was going in this direction mostly. So now if I order these passbands in the order of the oxygen emission lines from the comet that contribute, so starting with the low ionization stages here, oxygen 3, passing up to oxygen 6. Then this is what we actually see from the comet emission. Then for these the low ionization stages is where we see like little or kind of emission that's very close to the nucleus. And then as we pass through the ionization stages, we kind of see a progression of this emission from close to the nucleus to being much greater in extent. So this, yeah, all of these images are just a snapshot at a single point in time in the different way. This is the egress phase after it had passed behind the sun, but we see the same thing no matter where it is. So this makes sense. As the material is close to the nucleus, then it's still lowly ionized, and as it gets further from the comet, it gets ionized to higher ionization stages, and we see it in these channels, and we see it kind of further from the comet. So the normal coronal heating would be the opposite direction. Apart from 304, the rest of the channels go in the other direction. So this kind of backs up the model, I think, to some extent, in that it wouldn't make sense for iron to be doing most of the emitting here, because we would expect the observations to be in the opposite sense. So I think this kind of proves that it's oxygen that's contributing mostly to what we see from the comet. That's the model of why we think where the emission comes from, why is it bright in certain channels at certain times. But what can this tell us about the sun itself, which I think is a little bit more interesting, but it depends on your field, I suppose. I've just highlighted 4 topics to go into in a little bit more detail here. So can we learn about the density of the corona that the comet's passing through? Here's this is a similar image to what I showed before, and I've highlighted a couple of areas here in red and blue. So from independent measurements of the corona, this is from MHD models done by the predictive science group. They predict that this region of the corona is about 10 to the 7, and this part up here is like more like 10 to the 6. So we then look at what happens as the comet passes through these regions. We see that in this region, the material lights up and then disappears pretty fast. Up here, this material lights up but then stays bright for a long time. And if we do a intensity time plot of just the integrated light in each of these boxes, we see this. So this is time along here, and then for in that red box, the emission goes up, peaks, but then it goes back to the background level very fast within a couple of minutes. But for the blue region, intensity peaks, and then from here until it gets back to the background level is around 40 minutes before it returns again. So this image is in the 171 channel, so if I just remind you of what emission lines we expect to see here, it's mostly oxygen 5. So I'll then show you what our model predicts for how long each of these ionization stages of oxygen survives. This is what we have on the bottom. So this is for a coronal density of 10 to the 7, which is what we see in the red box, and then for 10 to the 6, where is the blue box. Then these are just the fractional abundance of each ionization stage of oxygen. And I've highlighted in red oxygen 5, which is the main emitting ion here. So for a relatively high density, the oxygen 5 emission is formed pretty fast, but it doesn't last long because that oxygen 5 is subsequently ionized to oxygen 6 and oxygen 7 through collisions with the electrons in the corona. For the lower density case, we don't have as many electrons in the corona, so this ionization takes longer. So the oxygen 5 lasts, stays around for longer, and that matches up with the observations. Yes. No, not yes. Yeah. Yes. So it's hard to the densities of the corona here are just kind of got large error bars on it, so it's difficult to kind of quantify the exact time range of this, what we would expect from the model, but we see the right behavior. So there can go some way to kind of verifying other models of the corona to see if we see the right density variation that other models predict. So what about the topology of the magnetic field in the corona? This is kind of like a different way to view the image, where I've just done call it a persistence movie, where as the comet passes through, we don't, I just kind of keep the brightest pixel from before, so you can see what's happening to the material as it comes off the comet. It's more obvious now that the comet is the kind of straight line here, but then as the material comes off, it interacts with the background magnetic field, and then up here it kind of goes in this direction, then it bends down, follows these structures here, and then up here it kind of moves up the way. So this must be telling us something about the magnetic field in the corona that the comet's passing through there. So how do we normally measure the field in the corona? Well, we can't measure it directly. You have measurements at the surface, and you do some sort of model that predicts what it would be higher up in the corona by interpolating what the magnetic field you do see on the surface. So the group at Predictive Science, led by Cooper Downs, did this sort of analysis where they've done a MHD simulation of what they think the magnetic field is in the corona, and then compared this with the Comet Lovejoy observations. So before I start the movie, this purple line here is the comet trajectory, and then these different colored dots are just test particles of ionized material as if it came off the comet at all these places. And then if their magnetic field model is correct, then these test particles should move along the field in whatever direction. So let's see how it compares. So this is the model, this is the actual comet emission, and then this is what their model predicts that emission should look like. So you can see it does well in some places and badly in others. Like here, they predict that the emission should move this direction, but it always moves down here. Looks like it does a good job here, and then it kind of kinks up again here, so they don't see that. So this is a good way to kind of verify these magnetic field models to see where they're doing a good job and where they're doing a bad job. Yeah. What moving down the? Yeah, I mean there's some sort of projection effect, but yeah, in some cases it's moving towards the sun. What's happening? Like they have the magnetic field at some sort of angle to the motion of the ionized material. So the material comes off the comet, gets ionized fast, and then it kind of, if it was perpendicular to the field, it would just kind of gyrate around the field line and not go anywhere. But if it's at an angle, then it kind of follows, it gyrates around the field line, but also follows the field as well. So it just depends on the orientation of the field compared to the trajectory of the comet at that point. No, yeah. And then this is the same thing on the egress phase. And the model does a little bit better here, and that's mostly because they have better input for their model, because to model the ingress phase, you need kind of the surface information, kind of a rotation before it comes back round. But for this side of the sun, you've got the magnetic field in the surface of the sun kind of more close in time to when you model this area. So the model does a better job here. You can see it kind of predicts that the material moves up here and down in this section. The duration time kind of does, because if it's sharply sloped, then the material moves along it fast. So it's kind of, as it's passing along the field, it's also dispersing to some extent. So that also contributes to the emission going down. But like here, the material moves up a little bit, but it stays pretty steady, and that's the field there is very close to perpendicular, so the comet material doesn't really have anywhere to go, so it hangs around in the same place longer. Okay. So then the last 2 points, I've kind of put a question mark, because this is things that I think we probably should be able to do, but I'm not convinced that we've actually done them yet. But there's kind of promising avenues to pursue here. So can we learn about the strength of the magnetic field firstly? You see here, you see kind of, apart from these striation motions, patterns, you also see this stuff kind of moving back and forth. And if I zoom in on a little section along the path somewhere around here, and then I put these white lines just kind of to guide the eye. But you see these striation patterns, they don't always move in the same direction. Like you see them kind of move backwards, forwards and backwards. So what's going on here? This is a cut just along the trajectory of the comet. So this is time and the emission intensity along the path. So what you see is, as well as the material moving back, it starts off, material comes off, pushes against the field, and then reverses and springs back again. And that's, you see these kind of turnover parts here. So this 500 kilometers a second is the trajectory of the comet, and then this material pushes back at about 50 kilometers per second in the opposite direction. So if we get a strength of the magnetic field here, we need to know how much material is coming off, how much that impinges on the field, pushes it, and then the field pushes back again. So it's pretty difficult to kind of quantify this, and that's why I put a question mark on the question before, because all we've done so far is just kind of show that this definitely happens, but the error bars on things like how much material is coming off the comet in the first place are huge. We also don't really know the magnetic field itself here very well. The kind of field lines it passes through are also be influenced by the other magnetic field round about them. So it's difficult to put numbers on this yet, but I think this is one area that we could pursue further. Okay, so then my final point was, are there density fluctuations in the corona? And this is just a hypothesis right now. But one of the most striking things from the observations is these kind of striations that we see. We don't see them all being a homogeneous emission as it goes through. So what's causing this pattern? I think there's two probable explanations. One would be that the material is coming off the comet itself in like a bursty fashion, where we see more emission when more material comes out, so it kind of bursts and then stops and then bursts again. But if we take a cut along just one section of this, we see that it's very periodic. I don't think this shows up too well, but this is just intensity along this slice. So it kind of peaks, very, very periodic. This is about 8 megameters between each successive bright peak. So it's difficult to envisage a mechanism whereby the comet would be bursty in such a periodic fashion like this. Comets will rotate, so that explains some like kind of periodic emission that you see further from the sun. But that rotation is typically the order of days. And to explain this emission, the rotation has to be like far too fast for the comet to be able to survive. It would break up if it was rotating anywhere near as fast as this. So it's not clear what mechanism would cause such a bursty sublimation of material like this. So then another explanation could be that it's the background corona itself that has some sort of periodic fluctuation in density. If the material passes through kind of higher density regions, then the comet material ionizes faster, and then we see it bright in these emission lines. And then if it's going through kind of low density regions, it takes longer for that material to get up to the high enough ionization stages for us to see it. So I don't want to say which of those explanations I think is more likely, but this could put some figures on what the density fluctuations we see. It would need to be something like a factor 5 fluctuation in density to explain this density, this emission fluctuation. So that's all I've got. Just to summarize, we see comets emitting in the EUV, which was a surprise before we launched STO. This was not something that anyone ever expected to see. And with most of the emission that we see comes from oxygen ions of various ionization stages. So the comet probes regions of the corona that normally look very quiescent and we don't really see anything. So it highlights regions of the magnetic field that are not normally visible by typical traditional means of observing the corona. So these Kreutz sun grazers, there's like thousands of them now. I think it's not unlikely that another few bright ones will be visible and throughout the life of AIA at least, and hopefully they can give us more information on the corona that they pass through.
Questions for Paul?
Those density striations you see, could those be I mean, you have a 12-second sampling cadence with AIA and a 2-second ionization time scale. They correspond to the
well, if you see the lines in the other direction, like this way, it's harder to see them, but that's the 12-second cadence of AIA. And not these lines in this direction, these kind of smaller ones that way. That's the AIA. That's the 12-second sampling.
It's all really interesting. I wondered about. I'm sort of wondering about the solar wind, and would you expect? I mean, these probably aren't. It isn't probably passing through high-speed solar wind, because there aren't many coronal holes probably around, but it's interesting how the material, it seems like once you deposit it, especially the longer term ones there, do you think that, do you see any drift that you can attribute to the solar wind, or is it all just sort of gyro resonance along the field lines?
Most of the time, this is closed field lines. Like down up to about here is closed field lines. So this stuff will just kind of, it'll eventually disperse so that it's kind of, it's kind of insignificant, but it'll eventually move down here somewhere probably. These lines are thought to be open field lines according to the magnetic field models. So yeah, so this material will join the solar wind, but can we observe that at like 1 AU? I think is like kind of very unlikely. But
a bit worried about what our friends in Warwick will do with those density diagnostics, if you know what I mean. Steve's laughing. The old kink mode debate. can you tell about what's inside and outside, what the structure of those field lines looks like with respect to them? I'm just wondering if they've seen these analyses and what they would say. I mean, we also have probably comp observations that go with this thing. It's actually interesting to look at what kind of wave species live in that area. So that's something for further study, but it'd be interesting to see if those density ratios crossing the field are strong enough to support a
just a plug for models. That there are some turbulence models of the corona that do show up, that do predict similar separations and density fluctuation magnitudes at those heights. Papers, John Raymond did some of the analysis of the density fluctuation stuff, as far as predicting the lengths of the little diffusive trajectories. I think he got a lot of that, not so much from the solar wind velocity or wave velocities, but just from the diffusion of material that is launched off the comet at a certain characteristic velocity. These dissociation events and successive ionization events have characteristic velocities with them that I've never understood really well, but those seem to match pretty well. But yeah, no, I think there is pretty good evidence for these density striations pre-existing. Most of the observations that we see are line of sight, so these tiny little things get smeared out. So this is a nice little probe of one little trajectory. Anyway, yeah, we could debate about how good are the models, but spacing does seem to be the extrapolation of the turbulence correlation length from the surface out to the extended corona, and the magnitude seems about right too.
Really interesting stuff. I have a couple of questions. Why don't we see any signs of shocks or the generation of waves out of the, this thing plowing through this medium? I mean, if it's entirely neutral, I can understand why, but you're telling us there's a lot of mass being shed that's ionized. And then the other thing is, let's see. Oh yeah, it seems as if in the absence of spectroscopy, you sort of have a relatively convincing argument that you think this is oxygen, but I think that it's obvious that water vapor can get through photo absorption out of the comet. What's not obvious to me is how you get ion out of a comet. I don't know what you're assuming with regard to the way that material gets shed from the comet as it goes into towards the sun, and so those are just the 2 points I wanted to make.
Iron oxide is pretty common, and there's, I can't remember the exact molecules, but there are a bunch of iron-containing molecules there. So they've been seen in not in comets as close to the sun as this, but they've been observed further out. But in terms of the shock stuff, I'm going to Glasgow University next month to talk to John Brown about this, because he's got all sorts of ideas about what should be happening with shocks there. So like in the plane of the sky space, like about 500 to 600 kilometers per second.
Yes. Oh. Thanks, Paul, again.